Okay, so my goal today is to describe for you the Lucy Knight experiment, if you don't know about it already, and to give you the kind of latest status on the program. This is a list of co-authors up here who are notionally our Lucy Knight team. Okay, next slide. Oh, okay. No, this should change the slides. Doesn't seem to. The arrows. This works. Okay, can you do it? Next one. Oh, okay, good. So Lucy is a program that was proposed to the LSITP program in support of CLIPS. And it was initially proposed as basically a bunch of flight spare hardware from earlier programs from Parker Solar Probe and from Stereo. And along the way, we got split into two separate payloads. One payload is called Lucy Light, which is going on the CLIPS CP12 mission. And that has a simple radio astronomy experiment on it, basically a knockoff of Parker Solar Probe, 20 megahertz baseband radio receiver, and it's really focused on doing plasma physics on the moon and magnetotellurics on the surface of the moon in coordination with Bob Grimm's LMS experiment. That's not the one I'm going to talk about today. I'd like to talk about Lucy Knight. Lucy Knight is the primary payload on the CLIPS CS3 mission. We're going to the lunar far side in Q4 of 2026. On the Firefly BGM-2 mission. It's a collaboration with the Department of Energy, the U.S. Department of Energy, Brookhaven, and LBL National Labs. And it's essentially a pathfinder for low-frequency radio astronomy on the quiet lunar far side. So it's a 50 megahertz baseband full Stokes receiver system, and I'll tell you more about that as we go. Oop. Oh, I do want to say something about Lucy Light. So this is Lucy Light. We're going to the Schrodinger Basin at the South Pole, near the South Pole. We have a single vertical 7-meter monopole antenna that'll be connected to a radio receiver. We have magnetometry, and we have flux gate and induction magnetometry, and then we have a system like the LMS experiment that deployed on BGM, on the Firefly, the first Firefly mission, the ballistic double probes that go out onto the surface of the moon to measure the electric field at the surface of the moon, and it's all coordinated into one package. So we'll do something like LMS, but we'll also do a little bit of radio astronomy. So Lucy Knight is a more bespoke system. So this is a graphic of Lucy Knight. It's a cube, a 1-meter cube that sits on top of the Firefly Blue Ghost lander. We have 6-meter tip-to-tip dipoles that deploy outward in the plane of the surface of the moon, and we measure individual monopole and differential voltages on those antennas into a 50 megahertz Nyquist, so 100 megasample per second 4-channel radio receiver. The key thing about it is that to do this kind of radio astronomy, you need a really quiet environment, right? And the biggest devil in all this is always the lander itself, the spacecraft itself, or even your own subsystems. So what we do is we require the Firefly lander, to die after the first lunar day. So they get us there, commission us on the lunar during the lunar day, and then on the first night at sunset, they're required to mechanically pull the power off of their solar cells and short the battery out. So they're dead forever after that. And then we operate on our own and control our own electromagnetic environment. You see on the side of it, I don't know if I can point here, there's a radiator, a big radiator. So the real challenge here, as you see, if you've seen in the STMD list of challenges, is surviving and operating through the lunar night. We have battery power. We have a big knockoff of the Europa Clipper battery. So a 40 kilogram battery that we use to operate through the lunar night. We capture the heat internally with the MLI and stay warm through the lunar night with operational power. But then during the day, of course, we have the opposite problem. We have a heat pipe. We have a radiator that points to the black of sky, and we have to dissipate that heat. This is the real challenge of the program. You see, we also have our own solar panels. We have our own S-band comm system, which is a Prox1 relay, Prox1 S-band system provided by Vulcan Wireless. We're going to the moon we just learned last week that the launch date is no earlier than November of 2026 on a Falcon 9. So this is Firefly Blue Ghost Mission 2. You see in the center of that stack there, if I can point, is a relay satellite that's provided by the European Space Agency. The Surrey Satellite company is building it. ESA is supporting them. And that goes in the middle. That's our primary comm system, is ESA, and NASA has struck some sort of deal whereby we get free communications in exchange for the launch. And then on the bottom, there's another vehicle, the Firefly Blue Ghost transfer vehicle. And we have also a system on there that I'll describe at the end of the talk. This is our landing site. We're going to about 24 degrees south near the anti-meridian, 2 or 3 degrees off the anti-meridian. We had to choose north or south for thermal reasons. You don't want to be right on the equator, and you want to have the radiator asymmetric with respect to the sky. It's also favorable for comms, which are kind of focused on South Pole operations. And the landing site itself is, we believe, fairly well mixed regolith. We wanted to have regolith that was as uniform as possible below us, although it's still, I think, one of the major systematics of the measurement. So how are we going to calibrate this thing? Well, that Blue Ghost transfer vehicle that flies overhead has a transmitter on it. It has I think a 6-meter tip-to-tip dipole and a transmitter that will transmit a waveform that we have provided to them. So it's a waveform it's basically a pseudo-random sequence, so a frequency comb, and we have a copy of that waveform in our correlator on the spacecraft, our spectrometer, so we can correlate against it and bring it out in the signal. And as the vehicle flies over and traces out the sky above us, we'll use that to map our antenna pattern and to try to understand our absolute intensity calibrations, which of course are modified heavily by the regolith. So there's some cute little graphic there. And the regolith. The regolith is a problem for anyone who wants to do radio astronomy on the moon, particularly with dipoles that are in the plane of the surface. The regolith is a dielectric, and it's structured, of course. It has a boundary. The upper part, the superficial regolith has a one dielectric constant, and then below that you have impact ejecta and other things so there's a gradient in the dielectric constant as you go down. And if you look at what's known about it, these gradients are on the sort of 10-meter spatial scale, and that is precisely what we're trying to measure, right? That's 12 meters is 25 megahertz, essentially. So we expect to see reflections, features in the spectrum that are associated with those gradients below us on this frequency, in the frequency domain precisely where we're trying to measure. So we have one other tool to help us with that, and that is there's a Rashid rover provided by the United Arab Emirates that's flying along with us that'll operate during the first lunar day. And we have fitted that with a transmitter, and that transmitter will broadcast 4 tones between 10 and 50 megahertz. And as it drives away, we'll pick up those tones on our system, and we can use it as a kind of bistatic radar system and try to measure the interference pattern of the intensity as it drives away. So this is like was done on the Apollo 17 mission. I think I'm almost done. Just a baby picture. So where are we now? This is the system that's in my lab about a month ago or so. This is what it looks like all built up before it is blanketed. We have delivered it to SDL in Utah, at Utah State, installed the radiator and the vibrator. We did the radiator and the solar array. We did vibration testing on the week of the 16th of June, and that was all successful. And we put it into thermal vac last weekend. We did the rough pump last weekend. We're in high temperature right now. We did a hot soak yesterday to test the battery up to 55 degrees or so, and that seems to be working. And we should be out of thermal vac by the first week of August. We have a little bit more performance testing to do, and then we ship it to Firefly by September 31st. So launch is, as I said, Q4. Landing is a month later. And what should we do next? This is my pitch. I think the thing we should do next that would be reasonable and realistic is to propose a 2-element interferometer to land nearby to Lucy. The site around Lucy will be reasonably well known. Lucy Night will be reasonably well known after we've done operations there. We'll have some ideas about the dielectric properties of the regolith. We'll have some ideas about the landscape, the terrain, the lines of sight. And if you have a lander rover pair where you drive the rover away from the lander, you can do both the magnetotellurics, again, the bistatic radar, but you can also do interferometry on a variety of baselines. Make measurements as you go away, make measurements as you come back, circle around, fill the UV plane, and this allows you to make maps of the sky that are, sort of a few degrees resolution down to the free cutoff feature in the galactic spectrum. Did I stay on time? Good. Okay, that's the end. Thanks.